In the final portion of the module, I want to go into greater detail about specifically what critical values are, and by this, I'm talking about z-statistics and t-statistics, and more importantly, how that relates to the hypothesis test that we're conducting. And there's a couple of different ways that we can think about this, and I want to relate it to previous concepts that we've talked about, like confidence intervals, because I think that helps us better understand exactly what we're trying to achieve here. So again, like you can think about a test statistic about it as like whether or not you should be surprised enough that you're getting such an extreme value given what we think the actual critical value should be, right? And if we're looking at a two-sided test, we're going to use the absolute value. If we're looking at a one-sided, we'll look at one side. But if that test statistic is bigger than whatever critical value we've assigned, like let's say the mean is 0.5, right? That's going to equate some sort of critical value. And we can then say, based on how extreme that is, whether or not it's likely that that is the true underlying value of the parameter. The biggest thing to remember, which isn't going to be too much of an issue for you because you're not actually going to be taking exams in person where you may be thumbing through a Z or a T table, but you do need to remember in R whether or not you want to multiply your p-value by 2, right? So you need to remember if you're calculating under just one tail or two. Because I can't stress this enough, there's going to be at least one person that messes it up, and I really don't want that person to be you. So make sure that you're calculating the right tail based on which hypothesis test you're running. Typically, the rule of thumb is that if you're going to do a one-sided test and the estimator is not in the region of the null hypothesis, do not multiply by 2 when calculating the p-value. So let's go back to our example before with female board members, but this time our null hypothesis is going to be whether or not the proportion of women on boards is above or equal to 0.5, with the alternate being below 0.5. In this instance, the test statistic is going to be in the region covered by the alternate and is not in the region covered by the null. So when we construct our z-score and we see that we have negative 23.57, remember that we're using a null of 0.5, so the smallest possible value that's covered by the null is not going to be the absolute value. We're only going to want to use one tail. In this case, it's such a high value that we're still going to end up rejecting the null hypothesis, but you can see that the p-value is in fact different than if we multiplied by 2 and looked in both sides of the distribution. Now, if you're doing a one-sided test and the estimator is in the region of the null hypothesis, you still don't want to multiply by 2, and you want to be specific about which tail that you're going to choose because you need to make sure that you're getting an answer that's larger than 0.5. I think this will make sense in a second. So again, going back to the example, if we think and want to set up our null such that mu is actually less than or equal to 0.5, our alternate or like true underlying belief would be that the proportion is actually greater than 0.5. And I think we all know that that's not going to be the case. But in order to prove that or find sufficient evidence for that, we're going to have to set up our one-sided test appropriately. So in this case, the test statistic is not in the region that's going to be covered by the alternate hypothesis, right? Like we don't anticipate that it's going to be above, the true proportion is going to be above 0.5. We go ahead and calculate our z-score in the exact same way, so we get the same z-score, but the way in which we calculate this is totally different, right? Because we're looking in the lower tail, so our p-value is very, very high, which means that we do not find sufficient evidence to reject the null hypothesis that the true proportion is above 0.5, which makes total sense, right? Now, finally, to wrap up, I want to take a look at how confidence intervals and null hypothesis testing overlap with regard to how we're considering the estimate and the true underlying parameter of interest, right? So when we're constructing a confidence interval, we may have some sample mean, and we construct bounds of uncertainty around that. When we're doing hypothesis testing, essentially what we're doing is we want to construct bounds of uncertainty, but those bounds are going to be around some parameter under the null hypothesis. Now, we can go about doing this in two different ways, but what I'd like to stress is that there is some overlap here, and I'd like to walk through that with an example. So, for instance, according to a union agreement, the mean income for all these assembly workers at a senior level is $525 per week. A representative from a women's group decides that they want to investigate whether or not there's any discrimination that's going on. And so we're going to allow mu to represent the mean income for female workers. And we want to determine whether or not this matches the norm of male workers. This representative gets a random sample of 36 female employees, and the mean pay per week is $495 with a standard deviation of 75. So let's go ahead and just use a confidence interval approach to see whether or not this is correct. We can construct our confidence intervals as such, and we find out that our 95% confidence intervals around the proportion of senior level assembly line workers is 500 to around 550. Now, this does not correspond with what women make on average, right? The average woman was making $495 a week. And since this falls outside of the 95% confidence interval of senior level employees, we can reject the null hypothesis. We can go about this also in a different way, right? We can look at putting confidence intervals around the amount that women make and see whether or not the mean for all senior level employees falls within that bounds. And what we'll find is that is not the case. And so again, we're going to reject the null hypothesis here. All this to say is that we can use this approach with confidence intervals, or we could set up a more traditional hypothesis test that we talked about today, and we'd end up finding the exact same answer, that the female employee mean weekly pay was different than the average senior level pay.